Hello guys, welcome to my YouTube channel Vishwaguru, a problem solver. Today's class we are going to discuss a numerical on the topic analysis of perfect frames by using method of joints and method of sections. This numerical first we are going to solve by using method of joint, then by using method of sections. Okay, here a cantilever truss numerical is given. The previous videos we have discussed that the numericals on simply supported trusses. The difference between simply supported and cantilever frames or the reactions. Here you can see, as it is a cantilever truss or frame, here there is no supported ends. Okay, this side is fixed, rigidly fixed. Here there is no supported ends. In case if there is no supported ends, then there are no reactions and there is no reaction calculation is needed. Okay, that only the difference between simply supported frames and then the cantilever frames. Okay, here no supported ends such as simply supported frames and no reactions, so no reaction calculations. Okay, so here first we are going to solve by using method of joint. Okay, method of joint means here we know that from each joint we consider the free body diagram and we will consider, okay, we will consider each joint should be in equilibrium. Okay, and we know that in method of joint we will use two equilibrium principles: algebraic sum of the vertical forces equal to 0, algebraic sum of the horizontal forces equal to 0. Okay, in method of section we use the third principle of equilibrium, that is algebraic sum of the moment about any point in the truss or frame that equal to 0. Okay, so here first by using method of joint we can start from any joints, preferably the joints at the corner. First I am going to start the free body diagram and the force analysis on the joint A. Okay, so first I am going to analyze the forces which are all acting on the joint A. Okay, so first I am going to draw the free body diagram of joint A. Okay, here you can see this is joint A. From the joint A, a downward point load 10 kilonewton is acting, and then this joint A is connected with two members such as AB and then AD. Okay, so for the free body diagram A, 10 kilonewton the point load will act, and then forces in the members AB and also AD, that two forces also will be there. Okay, so the free body diagram of the joint A, 10 kilonewton that is going to act exactly downward. Then a horizontal member, this force in the member AD that is going to act horizontally, but the direction as of now is not yet calculated. And there is an inclined member, that AB, okay, force in the member AB. So this 3, and then here we can see this angle is 60 degree. So this is the free body diagram of joint A. Here you can see, as we discussed earlier, we can use the two principles: summation of vertical forces equal 0, summation of horizontal forces equal 0. Okay, here the horizontal member, force in the member AD, that incline, there is a force in the member AB. Okay, so first I'm going to analyze algebraic sum of the vertical forces equal to 0, since the joint A should be in equilibrium. Here the TAB, that is an unknown incline force. 10 kilonewton, that is a vertical force. We know that the 10 kilonewton, that is a vertical force that is acting downward. This should be compensated by an upward force. Here, there are two forces. The TAD, it is exactly an horizontal force, so it cannot cancel a vertical force. TAB is an inclined force, so we can resolve this into two components, horizontal and vertical. So the vertical resolved component of TAB, that only can cancel this downward force 10 kilonewton. Okay. Here, this TAB, there are two possibilities are there. For the understanding purpose, I'm going to draw both the possibilities. Okay. This TAB is acting like this with respect to the horizontal 60 degree. Okay. In case if this acts towards downward, okay, for understanding purpose, I'm going to consider both the consideration. Then this TAB, if it act inwards to the joint A, then we can resolve this into two component. The horizontal component TAB cos 60, that will act towards right side. TAB sin 60, that will act exactly downward. So here you can see the 10 kilonewton already a downward force. This should be compensated by an upward force. But if you consider this TAB is acting inward to the joint A, okay, like this, then the TAB sin 60, the vertical resolved component of TAB, that is also I will act exactly downward, so that cannot cancel that 10 kilonewton. Okay, so the possibility of this one is wrong. Okay, so it cannot act in the fourth quadrant. Then the next possibility, okay, that means the next possibility, that is it may act outwards from the joint A, okay, like this. Then we know that here from the joint A, the TAB, if it acts outwards from joint A, then the vertical component TAB sin 60, that will act exactly upward. Then the horizontal component TAB cos 60 degree, that will act towards left side. So here, if you consider this TAB is acting outwards from the joint A, then the resolved component TAB sin 60, that will act upward. So that is going to cancel this 10 kilonewton, or the downward force 10 kilonewton equal to upward force TAB sin 60 degree. So from this, we can calculate TAB, that equal to 11.5 kilonewton. Okay, 11.5 kilonewton. From the point A, it is going to act outwards. So from point B also, it will act outward. Okay, so here you can see it is going to compress. It is going to compress the member. So it will be compressive in nature. Okay, so it is compression. Okay, so then summation or algebraic sum of the horizontal forces equal to 0. Here you can see this 10 kilonewton, that cancel the vertical component TAB sin 60 degree. Okay, then this TAB cos 60 degree, which is acting towards left side, okay, that should be compensated by another horizontal force, that is TAD. If this act left side, then this should act towards right side. That means like this. Okay, so we can say algebraic sum of the horizontal forces 0. So TAD that equal to TAB cos 60 degree. Here the TAB, the value already we calculated. If you substitute and simplify, we will get the value of TAD that equal to 5.75 kilonewton. Okay. Here you can see this TAD. Here for the free body diagram or joint A, it is inwards to the joint A. So for point D also it will act inwards. Then this is going to tend to pull the body, the member AD. So this will be tensile in nature. Okay. So now the forces in these two members, AD and AB, these two we had calculated. Then these two we are going to calculate. Okay. Next, the forces in the member. That means forces with respect to the joint B that we are going to analyze. Okay. Now there are two unknowns. To calculate the two unknowns, I am going to consider the joint B. Okay. So here, first I am going to draw the free body diagram of joint B. Forces in the member BC, BD and BA. This is going to act with respect to or from the point A. Here, the tension or forces in the member BA, that already we know the numerical, that means magnitude wise 11.5 kilonewton, and direction also we know. These two, BC and BD, these two are unknown, direction and also magnitude. Okay. So the free body diagram of the joint B, it is having one horizontal member, that is force in the member BC. Okay. Then one inclined member, force in the member AD. Then another one inclined member, that is forces in the member AB. Here this one direction wise known value. Okay. And here you can see with respect to the horizontal, this is 60 degree. Then this is also 60 degree. Because you know, if this is 60, then we can write this angle that also 60 degree. If this is 60 degree, with respect to B, this TAB, that also will act an angle 60 degree. Okay, so these two inclined forces are acting horizontal from the point B with an angle 60 degree. Okay, so here, this is the known value, direction wise and magnitude. So first I am going to resolve this inclined force. Okay, that is, this is TAD as we discussed in this diagram. From the point B, if you draw an horizontal, this inclined force makes an angle 60 degree. Okay, this is TAB. So if I resolve the vertical component that will act downward, TAB sine 60 degree, the horizontal component will act towards right side, TAB cos 60 degree. Okay. So this TBC, that is exactly a horizontal force. These two are the inclined forces, that is TAD and TAB and TAD. Here TAB is the known in magnitude and direction. When you resolve, we got a vertical resolved component TAB sine 60 degree, which is acting downward. To compensate this vertical resolved component, we need an upward force. Here TAD, there are two possibilities are there. In case if it acts downward, that means like this, in the third quadrant, then the vertical component will act like this. That is also downward. So that cannot compensate this TAB sine 60. Do you understand? If this TBD, that inclined force, if it acts like this outward from the point B, that means in the third quadrant, if it acts in the third quadrant, the TAD sine 60 will act downward. Here, this TAB sine 60, the known one, that is also downward. So this cannot cancel. So this TBD, that will not act. Okay, this one TBD. Okay, TBD will not act. Just to erase this. This one TBD. Okay, from the point B, D. This TBD will not act downward. It should act like this, inwards to the point B. If this TBD acting inwards to the point B, then we will resolve this into two components. As I mentioned earlier, this TBD is acting 60 degree with respect to the horizontal. So I'm going to resolve that one, TBD. So the horizontal component, this one 60 degree. So TBD cos 60 degree. The vertical component TBD sine 60 degree. Okay, TBD cos 60, TBD sine 60. Now, if you analyze summation of the vertical forces equal 0, the TAB sine 60, that is a downward force. TBD sine 60, that will be an upward force. Okay, so TAB sine 60. Okay, this is TAB sine 60. Okay, that downward force equal to TBD sine 60. TBD sine 60. Here you can see the sine 60 we can cancel. So TAB equal to TBD. The TAB we calculated already. So the TBD, that also 11.5 kilonewton. And here for the point B, this is inward. So for the point D also, it will invert. So here you can see this will be tensile in nature. Okay, so this is tensile in nature. Okay, then algebraic sum of the horizontal forces equal to 0. Here you can see there are three horizontal forces are there. Actually, here there are three forces. TBC, horizontal force. Okay, that is direction wise unknown, magnitude also unknown. TBD, one incline. So we have a resolved horizontal component TBD cos 60, that is towards right side. TAB, that is one inclined force. So the horizontal resolved component TAB cos 60, that is also horizontal. So this is also horizontal. This is also horizontal. So, but both are acting towards right side. So this TBC, that should act definitely towards left side. Okay. So here you can see the TAB cos 60 degree. TAB cos 60 plus TBD cos 60. Okay, these two are acting towards right side. This should be equal to, okay, this to be equal to this force TBC. If these two horizontal components are acting towards right side, so this TBC that should act definitely left side to compensate these two horizontal forces which are all acting towards right side. TAB cos 60 also right side. TBD cos 60 also right side. So to compensate this, TBC should act left side, that equal to TBC. We have the value of TAB. We have the value of TBD. But here you can see both values are same. And cos 60, we know that 1 by 2. So TAB 1 by 2, TBD 1 by 2. So both values are same. So we will get the same answer. Okay, that means the TBC, we will get 11.5 kilonewton only. So the TBC equal to 11.5 kilonewton. And here from the point B, it is acting towards left side. So from the point C, it is acting towards right side. So this will be compressive in nature. Okay. So now all the forces we calculated. Okay. Then we are going to calculate, that means substitutes or interpret into the force table. Okay. Finally, the force table. Okay. That means we are going to tabulate the results. Serial number, then members. What are all the members are there in the truss or frame? Then magnitude of the force in terms of kilonewton. Then its nature, whether tensile or compressive. First one, the member AB. The value we calculated as 11.5 kilonewton. And here you can see the AB is compressive in nature. So compression. Okay. Then second one, the member AD, we calculated the value 5.75 kilonewton. Here you can see this AD, that is tensile in nature. So tension. Then the third member, that is BD. This is also equal to AB, 11.5 kilonewton. Here BD, you know that tensile in nature. That's why that will be in tension. Then the last member BC, this one, the value is 11.5. Here it is compressive in nature. So 11.5 kilonewton. Then it is in compression. Okay. Okay, guys. I hope you all understand this video. Actually, this is part 1. Here we discussed this cantilever truss by using, that is, method of joint. The next video, same numerical, we will discuss by using method of sections. Okay. I hope you all understand. Thanks for watching. And don't forget to subscribe my YouTube channel, Vishwaguru, a problem solver. Okay, guys. Thank you.